Hello, let us solve this nozzle problem using TESTcalc. So we have carbon dioxide entering the nozzle, let's say at state 1. The inlet state is completely supplied, and the exit state is also given, and we are also supposed to find the isentropic exit velocity. So therefore, let's use two different states. One is the real exit state, we'll call it state 3, and 2 would be our isentropic exit state. So we'll solve essentially two different nozzle problems. So let's launch the TESTcalc. We follow the system track, system open, generic, single flow, and let's use the PG model as the problem dictates, the perfect gas model. And that launches our TESTcalc. First order of business, select the working substance, which is CO2. What do we know about state 1? Pressure is given, temperature is given, the velocity is given. And that is it. So we don't know the mass flow rate yet. But about state 3 we know a lot. So let's in advance write down the mass flow rate will be m dot 3. So in other words, if I hit a calculate button, the white background tells us that we don't know mass flow rate yet. So once we calculate state 3, we'll come back here and calculate the mass flow rate. At that time, area also will be calculated. So let's go state 3 directly, which is the actual exit state, 100 kPa, 1400 Kelvin. We don't know the velocity, we better make it unknown. And the area is given to us is 10 centimeters square. Also, that is not sufficient to find the state. We need one more information, and that comes from, of course, the energy equation for this nozzle. And just to revisit, the energy equation is simply for any open system, any open single flow system, that's the general energy equation. Steady state means the picture of the system doesn't change with time, so the total energy, total entropy, etc. of the system remains constant. And by the way, our boundary here is the system's universe. So therefore, there is no heat transfer, it's an adiabatic nozzle, no external work. So that gives us J1 equals J3 as our energy equation. Coming back here, we put J3 equals J1, and now the exit velocity is calculated for us. To find the entropy generation rate, we come to the device panel, load the state 1 and state 3 as our inlet and exit state for the actual nozzle, no heat transfer and no work transfer. Calculate, and this produces the entropy generation rate, 0.0113 kilowatt per Kelvin. And now the final part, to go and calculate the isentropic state, state 2, which is the easy one to do. Again, the exit pressure is the same as the real nozzle, and entropy remains the same, and the flow energy remains the same as dictated by the energy equation. Notice that if the velocity was given, then you could not enter J because it will be over specification of the problem. So you have to first make velocity as an unknown, and now we can calculate, and of course the mass flow rate would be same as equal m dot 1. Oh, let's go and make sure m dot 1 is known, because m dot 1 equals m dot 3. If I do a calculate, now the background becomes green. So state 1 is now completely known, and m dot 2 in terms of m dot 1, if I do a calculate now, the background becomes green. That means m dot 2 is now known. So notice we have found the exit velocity, also the exit area, which is not anymore 10 centimeters square. Now this nozzle is shaped differently because it's isentropic, and it shows that the exit area now is different. There are many other features of TESTcalc. Suppose if we, first of all, we can show the calculated states on a TS diagram. And if you draw a constant pressure line, this is the 200 kPa line and 100 kPa line. You can see exactly as you expect the actual nozzle. You can see entropy increasing, and the real nozzle, the isentropic nozzle, of course, you can see the vertical line, which is isentropic. So some of the features could be, if you click the super calculate button, I'll just highlight one little feature, that it will produce the detailed output, but more importantly, a few lines of code, which is called the test codes. Essentially, these are what are known about the problem. Suppose you copy this code and save it for later use. I can show you how it can be used. Because this is perfect gas and ideal gas models are kind of cousins of each other, then we could go and use the same test code, because the known quantities are the same, for the ideal gas model. So again, if we go to the single flow system and launch the ideal gas model, where Cp is considered a variable, a function of temperature, go to the I/O panel, paste the test code, and then click the load button. And the load button is going to regenerate the solution instantly. And you can find all the states have been calculated again for CO2. But this time, as you can see, the answers could be slightly different because it's an ideal gas model. You can see that velocity is different now, 513 as opposed to 411 that we found. Quite a substantial difference. That's because the temperature is so high in this particular problem that the ideal gas and perfect gas model results vary significantly, because ideal gas incorporates the dependence of Cp on temperature. So I'll stop here and let you play with it. You can change, let's say, inlet pressure to see how it affects. You can change inlet temperature to see how it affects the exit velocity, and many other interesting studies you can do on the fly.